let's learn how to calculate the voltage of a galvanic cell. So for our first example, we are going to calculate what is the voltage of a cell that has this this redox reaction going on. Zinc solid plus copper 2+ aqueous reacting to form zinc 2+ ions and copper solid. And I'm not going to write this down, but we're going to assume this is a standard cell. So when we are being asked to calculate the voltage of a cell, the voltage comes from the difference in electrical potential between the cathode and the anode, between the reduction and the oxidation. So for us to be able to answer this question, we need to know what is the potential of the reduction and what is the potential of the oxidation. And then once we know what they are, we need to know what their difference is. So what's the difference between them? The first thing that we need to do is figure out the potential for each of these half reactions. And I'm going to not fully write the half reactions out, but just a little bit. So we're just going to start. One of the half reactions we know is going to involve the zinc, and the other half reaction is going to involve the copper 2+ ions. And there's going to be more than that, but we're just going to start with that. So first thing that we have to do is go find the potentials of these half reactions. And what I have made for you are two tables. So these are ALEX data tables. And first of all, like usual, it's really important when you're doing problems on ALEX that you use ALEX's data, that you don't use anybody else's data. Otherwise, your answer might be wrong because there might be slight differences in the voltage. So second of all, because it's so tedious to have to reopen the data tables every single time you're solving a problem on ALEX, what I've done is copied the ALEX data table and then put them on Canvas for you so you can download them and you can just have them all the time. And the data tables, the reduction reactions are organized two ways. The way that you're looking at right now, is organized by voltage. So at the top of this table, you're getting the half reaction with the highest voltage. And then as you go down the table, the voltages get lower. Here's our hydrogen. This is our baseline, what we define as 0. And then they go down in that way. And so sometimes it's useful to have the data in this particular format. And then I also have for you the voltage sorted alphabetically. So here they're not in numerical order, but they're in order of these atomic symbols. And sometimes it's easier to look for the data this way. They're in both of these forms on ALEX as well. So you're just going to pick and choose which data table you want to use based on if it's easier for you to search alphabetically or if it's easier for you to search numerically. For this problem that we're working on right now, it's going to be easier for us to search alphabetically because we don't know anything at all about the voltage, but we do know about the atoms that we're dealing with. When we go searching, we are not necessarily going to be able to find both of these as reactants because one of them is an oxidation reaction and the other is a reduction reaction, and the table only lists reduction reactions. So let's take a look at how that's going to work. We're looking for zinc and we're looking for copper 2+. Let's start with looking for zinc. That one's actually going to be easier for us to find. So here's our list alphabetically. We're going to go all the way down to the bottom for zinc. And here is our zinc reaction. There's only one zinc reaction. And what you'll notice is that our reactant, which is zinc solid, is on the right-hand side of this half reaction. That doesn't mean that it's wrong. It just means that our version of the zinc reaction is reversed from what's in this table. And you're going to have that happen with every single one of these examples that you do. So what I'm going to do is I've got the whole entire half reaction is right here for us. I'm going to take this half reaction. I'm going to use this information. So knowing that the other side of the arrow is zinc 2+ and 2 electrons. I'm going to start with that. Zinc 2+. and 2 electrons. And then what I'm going to do next might be a little bit upsetting. Bear with me. I'm going to take this voltage, negative 0.7618, and I'm going to copy that down over here in my notes. Negative 0.7618. Now you might be saying to yourself, that doesn't make any sense at all, because this reaction is not the same reaction as what is in the data table. It's actually reversed. So my reaction is reversed. Shouldn't I have done something with the voltage, like change its sign maybe, like we would do for other thermodynamic stuff? And no, don't. You're going to copy those voltages exactly the way they are in the table without making any changes to anything at all. Bear with me because you're about to see why. So we have found the first one. Let's go looking for the second one. So our second reaction is the copper 2+. And let's go find its voltage. Copper 2+, going to be up here with the C's. And here I have found the copper. There's actually 3. There's 3 copper reactions. So we need to be a little bit careful and make sure that we're picking the right one. This reaction down here, nowhere has a copper 2+ in it. This is copper plus going to copper, so we know it's not this one right here. So we've got it narrowed down to 2. It's one of these 2 half reactions. We have to figure out which one it is. They both have copper 2+ as a reactant, so they have different products, copper versus copper plus. Let's go look at our reaction. What are we actually making? We're making copper, not copper plus. So that's going to tell us which half reaction we need to use. We want not this one. This is going to be the correct reaction for us. Copper 2+ plus 2 electrons makes copper, and the voltage for this, 0.3419. 0.3419. Oops. 0.3419. So those are our 2 half reactions. We were able, so one of the things that's great about that table is that we were able to get the half reactions completed without really thinking very much, because we were able to look them up in the table. The table gave us the balanced half reactions, which is awesome. We're going to use that a lot. Also, we got the voltages out of the data table, and I'm gonna make a little always, so we are never change the E values. You need to use exactly as they are in the data table, not changing the signs or anything. So how do we actually use these half reaction voltages to calculate the voltage of a cell? So the voltage of a cell, let's make this a different color. The voltage of the cell, E cell, is calculated by taking the difference of the 2 half reactions. The way that we're going to do that is take the cathode half reaction and subtract from that the anode. Cathode minus anode. The half reactions, before we can plug into this equation, we need to figure out which is which. So let's go back up to our half reactions. Let's use oil rig as our trick. Oxidation is loss. Oxidation is where electrons are being lost and produced by the reaction. So this first reaction is our oxidation because electrons are being produced. Reduction is gain. Reduction is where we are adding electrons. So our second half reaction is our reduction. And once we know oil rig, then we remember the cat is red, red cat. So this is the reaction that is taking place at the cathode. And this is the reaction that is taking place at the anode. So we're ready to start plugging things into our E-cell reaction. The voltage of the cathode, 0.3419 volts, and the voltage of the anode. Now look at what's going on here. We have this negative sign built into our E-cell reaction. Since we did not change the negative sign when we brought that data off of the table, even though the reaction was backwards, the negative sign in our E-cell reaction is going to do the changing of the sign for us. So we do not want to change the values or the signs on our tabulated data because the E-cell equation has that built into it for us. And so this works out to be 1.10 volts. That is the potential, the voltage of this cell. 1.1 volts is how many volts are exchanged in this particular redox reaction. What you need to know, and we're going to see this come up a couple of times, is that the value of E-cell is always a positive number. It is never a negative number. So if you plug two numbers in to the E-cell and you get a negative number, A, you've done something wrong, and B, all that you've done wrong is plugged the numbers in backwards. E-cell is always positive, and this is because positive E-cell means that the reaction is producing electricity. And it is a spontaneous reaction, meaning that it's just happening on its own. If you were to calculate a negative E-cell, that means that the reaction requires energy. We are going to talk about reactions that require energy. Those reactions are called electrolysis, which you've probably heard of before. It's not the same as a battery. It's not the same as a voltaic cell, a galvanic cell. This is a reaction that is non-spontaneous. So your E-cell numbers are always going to be positive.